Sleep is often framed as a time of rest, but in the brain, it's also a period of intense physiological maintenance, most notably detoxification. One of the most critical systems involved in this cleanup process is the glymphatic system, a network that facilitates the flow of cerebrospinal fluid through brain tissue, washing away metabolic waste products such as beta amyloid, tau, and other neurotoxic proteins. This nightly rinse is essential to cognitive health, and disruptions to this process are increasingly linked to heightened risks of neurodegeneration, particularly in aging populations. Emerging research suggests that glycogen accumulation, especially if dysregulated, may play a subtle but powerful role in impairing the function of this detox system and, by extension, sleep quality itself. At the center of this relationship are astrocytes, the same glial cells that store brain glycogen and support neurons metabolically. During wakefulness, glycogen in astrocytes is gradually depleted as the brain consumes energy for cognitive tasks, movement, and sensory processing. Sleep is not only a time to restore mental clarity, but also to replenish these glycogen stores. This cycle of glycogen depletion and restoration appears to be tightly intertwined with the sleep-wake cycle, and possibly with sleep architecture itself, particularly the deeper, slow-wave stages that are most strongly associated with glymphatic clearance. When glycogen accumulation is abnormal, either due to impaired breakdown or excessive synthesis, the astrocyte's ability to manage energy and support detoxification may falter. Inefficient glycogen turnover can disrupt intracellular signaling, alter ion gradients, and limit the energy available for aquaporin 4 channels, which are critical gatekeepers for cerebrospinal fluid movement through astrocytic end feet. These channels are essential for driving the glymphatic current, and any energy shortfall in astrocytes can lead to reduced clearance capacity. Over time, this impaired detoxification may allow neurotoxic proteins to accumulate in brain regions tied to memory, emotion, and executive function. Moreover, abnormal glycogen handling in the brain may indirectly contribute to poor sleep quality itself. Disruptions in astrocyte metabolism can influence the release of adenosine, a sleep-promoting molecule that accumulates during wakefulness as a byproduct of ADP metabolism. Adenosine plays a key role in building sleep pressure and helping the brain transition into deep sleep. If glycogen is not adequately mobilized or restored, adenosine dynamics may be altered, flattening the natural oscillations that underlie restorative sleep cycles. This could help explain why individuals with metabolic dysfunction, such as insulin resistance or chronic inflammation, often report fragmented sleep, lighter sleep stages, or reduced time in deep sleep. In animal models, sleep deprivation itself has been shown to lead to compensatory increases in glycogen synthesis during recovery periods, suggesting that glycogen homeostasis is part of the sleep rebound mechanism. But if the regulation of this cycle is faulty, such as when glycogen accumulates in poorly branched or insoluble forms, it may not only undermine this recovery process, but also introduce metabolic stress. Malformed glycogen aggregates can interfere with astrocyte function, promote oxidative damage, and, in extreme cases, resemble the polyglucosan bodies observed in certain neurodegenerative diseases. These aggregates don't just block energy flow, they actively impair the glial infrastructure necessary for nighttime detoxification. There is also growing speculation that circadian rhythm disruptions may compound the problem. Brain glycogen levels appear to follow circadian patterns, with distinct cycles of synthesis and degradation. If sleep timing is irregular, due to shift work, jet lag, or late-night screen exposure, these cycles may fall out of sync, potentially leading to both metabolic and detoxification inefficiencies. In this way, disrupted sleep and impaired glycogen turnover may enter a harmful feedback loop, each worsening the other over time. Despite these concerning links, the picture is not entirely bleak. Glycogen metabolism, unlike genetic risk factors, is highly modifiable through lifestyle. Regular physical activity helps promote efficient glycogen turnover, improves insulin sensitivity, and enhances deep sleep. Diets low in refined carbohydrates but rich in polyphenol, magnesium, and complex fiber can reduce the risk of dysfunctional glycogen accumulation. Sleep hygiene practices, such as maintaining consistent bedtimes, limiting caffeine, and promoting darkness at night, may help preserve both astrocyte function and glymphatic flow. Ultimately, understanding how glycogen accumulation affects sleep quality and brain detoxification is part of a broader realization. The brain is metabolically fragile, and its nighttime cleanup crew depends on well-regulated energy reserves. Astrocytes, long overlooked, sit at the intersection of sleep, metabolism, and long-term cognitive health. When glycogen metabolism is functioning as it should, it supports the glymphatic system and ensures the brain wakes each morning cleaner and clearer. But when this system goes awry, toxins may quietly accumulate, sleep may lose its restorative quality, and the risk of cognitive decline may steadily rise.